The paper of the day is ZooKeeper, Weight-Free Coordination for Internet Scale Systems. This paper describes ZooKeeper, a service for coordinating processes of distributed applications. Since ZooKeeper is part of critical infrastructure, ZooKeeper aims to provide a simple and high-performance kernel for building more complex coordination primitives at the client. It incorporates elements from group messaging, shared registers, and distributed log services in a replicated centralized service. The interface exposed by ZooKeeper has the weight-free aspects of shared registers with an event-driven mechanisms similar to cache invalidations of distributed file systems to provide a simple yet powerful coordination service. The ZooKeeper interface enables a high-performance service implementation. In addition to the weight-free property, ZooKeeper provides a per-client guarantee of FIFO executions of requests and linearizability of all requests that change the ZooKeeper state. These design decisions enable the implementation of a high-performance processing pipeline with read requests being satisfied by local servers. The paper shows that for target workloads 2:1 to 100:1 read to write ratio, that ZooKeeper can handle tens to hundreds of thousands of transactions per second. This performance allows ZooKeeper to be used extensively by client applications. ZooKeeper has two basic ordering guarantees. First, linearizable writes. All requests that update the state of ZooKeeper are serializable and respect precedence. FIFO client order. All requests from a given client are executed in the order that they were sent by the client. Let's look at the evaluation. The paper performed all of their evaluations on a cluster of 50 servers. Each server has Xeon Dual Core 2.1 GHz processor, 4 GB of RAM, gigabit Ethernet, and 2 SATA hard drives. They split the discussion into two parts, throughput and latency of requests. To evaluate the system, they benchmark throughput when the system is saturated and the changes in the throughput for various injected failures. They varied the number of servers that make up the ZooKeeper service, but always kept the number of clients the same. To simulate a large number of clients, they used 35 machines to simulate 250 simultaneous clients. Now, looking at the latency of requests, to assess the latency of requests, they created a benchmark model after the Chubby benchmark. They created a worker process that simply sends a create and waits for it to finish, sends an asynchronous delete of the new node, and then starts the next create. They vary the number of workers accordingly, and for each run and have each worker create 50,000 nodes. They calculate the throughput by dividing the number of create requests completed by the total number of time it took for all the workers to complete. Now, let's look at the contributions of the paper. There are three key contributions. Coordination kernel. Paper proposes a weight-free coordination service with relaxed consistency guarantees for use in distributed systems. In particular, they describe their design and implementation of a coordination kernel, which they have used in many critical applications to implement various coordination techniques. The second is coordination recipes. They show that how ZooKeeper can be used to build higher-level coordination primitives, even blocking and strongly consistent primitives that are often used in distributed applications. Experience with coordination. They share some of the ways they can use ZooKeeper and evaluates its performance. Let's talk PS score for this paper. Overall, this paper is a good read, so it gets 9 out of 10 on readability. With 14 pages long, it scores 8 out of 10 on length. It's an analysis of an existing system with pretty good description, so that makes it 9 out of 10. Its industry value and learning meter is high, so it gets 10 out of 10 on each. Overall PS score is 9 out of 10.